The families of cubic equations. So far we've been looking at sketching cubic graphs. We've been able to factorize cubic graphs. We've been able to graph them in factorized form. But now we also need to be able to determine the equation given certain amounts of information. Now, if we were to use to find a cubic equation in its unfactorized form, that involves a lot of simultaneous equations, and ain't nobody got time for that. So we're thankfully, if we use some of the established templates that we know from our previous exercises, there's certain patterns that are bound to happen, then we can actually take some shortcuts and hopefully be able to find these equations very quickly. So as you can see here, we've got some various examples. So for example, if you would use this template if you've just been told the graph's been dilated and it's just been translated up or down certain units. If you've been told virtually nothing, if you've been just given, in this case, you would need 4 random coordinates, then I'm sorry, you're gonna have to do some simultaneous equations. Hopefully it would be a calculator allowed type scenario. Now these little friend here, you would use, this one here, you would use if you've been given a stationary point. So if you've been told where the point of inflection or stationary point is, you could just use this template and then sub everything into that, and hopefully hope all for the best. It works exactly the same way as when you use a quadratic. So the minus b is where it's moved left or right, and the plus k is where it's moved up or down. If you've been given 3 lovingly and jolly good x-intercepts, then you can use this one down here, which is splendid, and that is the greatest, because all you need to do is find the a. And alternatively, if you've mentioned or seen here, if you've got a turning point. Now, just so you know, in a lot of questions, they like to say that they're wanting to use this. They don't say there's a turning point somewhere. They'll say it just touches the x-axis, or it touches the x-axis. If you see the phrase touches the, then that's a turning point, is what we're going to be looking here. So let's get started. Enough of this waffle. Let's actually get some maths done. So find the equation of the cubic function for which the graph is shown below. We have got a turning point at 2, 0. We've got a random coordinate here. We've got an x-intercept at 0. So we can actually use that bottom, the one I've highlighted in that sort of red color there. We can actually use this. So I'm just going to mention here that we've got, so where's our x-intercepts? One of them is at 2, 0, and it's also a turning point. So that means that's going to be the bracket x minus 2 squared. Remember, if that was negative 2, 0, that'd be x plus 2 squared. We've also got an x-intercept at 0, 0. So therefore, there's going to be a coordinate. Well, I would normally write x minus 0, but of course that is just x. So far, we can actually start putting our equation together. We've got y equals a x brackets x minus 2 squared. Hooray, that's what we've got so far, because there's a lovely turning point there. Now we just need to know what this value of a is. A is a dilation factor, by the way. It's just how much it's been stretched or squashed down. So what I'm going to do to find this a, we've got this lovely random coordinate. Now, I'm going to use the random coordinate rather than the x-intercepts, because if you substitute, say, I don't know, 2 for x in here, you'll get a 0 and everything will get knocked out. If you substitute 0 for x, everything will get knocked out. So we don't want to knock out anything. That's why we have that random coordinate in there. So to substitute x equals 3, y equals 6 to solve for a. So 6 is equal to a times 3 times 3 minus 2 squared. So that's going to be 3 minus 2 is 1. 1 squared is, well, 1. So 6 is equal to 3a. A is equal to, we need to divide both sides by 3. 6 divided by 3 is, of course, going to be equal to 2. So therefore, my equation is equal to 2x brackets x minus 2 squared. There is my lovely, lovely, lovely equation. Splendid. So let's have a look at this next one. Find a cubic function whose graph touches the x-axis. As soon as you see the word touches the x-axis, that is a turning point. Because normally, the reason I know that is that the other words that they use to say, if it's just like an x-intercept, they'll say passes through the x-axis or has an x-intercept of. So the fact that it says touches indicates it's a turning point. Although it's very vague, I understand that. At x equals -4, cuts it at the origin. See, cuts it, there we go. So that's an x-intercept at 0, 0. And has a value 6 when x equals 3. So that means it passes through the random coordinate of -3, 6. So we can use the exact same template that we used before. So I know we've got an x-intercept at 0, 0, got a turning point at x equals -4. So what that means is that so far my equation will look like this. So just so we're aware, that's this bit, and this is represented here. So there we go, we've got our template. We just need to solve for a, so we're going to sub x is equal to -3, y is equal to 6, solve for a. 6 is equal to a times -3, brackets -3 plus 4 squared. So -3 plus 4 squared is going to make that +1 squared, which is going to be 1. So 6 is equal to a times -3 times 1. So that means 6 is equal to -3a. We divide both sides by -3, and we get -2 is equal to a. And so therefore our equation looks like this. And done.